good afternoon. My name is Khandekar, and I am professor in the Department of Mechanical Engineering. So, I am told that you are the TechUp fellows, so to say, isn't it? And you are all now located somewhere for 3-year program. Is that correct? I think there was one more batch which came before this, and this is the second batch. Okay. Yeah. So, I think I have only half an hour actually. So, I do not know. I mean, I tried telling the last batch some things, and I will try to sort of experiment with you also. I am an experimentalist. Anyway, so it's basically to talk about teaching in thermodynamics and heat transfer. Okay, and that is what I also teach. We have a core thermodynamics course, which is done by almost all across the institute, and we also have a heat transfer course, heat and mass transfer, which is done by the mechanical engineering students. It's a compulsory course in the 6th semester. Okay, the present semester I am teaching, in fact. And how many of you are trained in thermal or fluids? 1. Okay, 2, 3. Okay, most of you are MTechs. Or PhDs also? No, most of your MTechs.
Sir, I have submitted my thesis.
Oh, you have submitted your PhD thesis. Okay, so more or less. Okay. So anyway, so what I wanted to tell you was that look, thermodynamics is a vast course. So I don't know whether you will get a chance to teach or not. Heat transfer, of course, many of you may teach. Okay, depending on your interest also and the type of institute which you are in. And there are plenty of books which are available. Both of them are classical subjects, so to say. Okay, so plenty of books are available. Some of the books are user friendly, some are more matured, some are for more matured students or matured teachers, for example. Some of them are very user friendly. And right now, one of the most popular books which we are using here in IIT also is the thermodynamics as well as heat transfer, is by a professor called Yunus Şengel. Okay, so Shengel's book is pretty good. If you really devote your time reading it and try to now, why that book is good and why I also like it as a teacher, I can tell you that. 2 things. One is the book is very friendly. It talks to the students. I mean, it talks to the reader. Okay, there is a dialogue which sets up, between the author on. It's like a teacher itself. It's like a speaking. The other thing which is more important, okay, is the fact that 2 things are important. One is that the examples which the book gives are very realistic. Okay, that means the data which has been taken, the assumptions which are done, okay, the calculations which are done are very, very realistic in what goes on in the industry, for example, or what goes on in the market, so to say. Yes, in our surroundings. So that is one. The second thing is that it picks up, that word is important, surroundings. It picks up concepts from around you, isn't it? And then tries to put the theoretical framework and give those examples and then connect the two. So I think it is very, very, very important as a teacher, okay, that the subject which you are teaching, whether it is thermodynamics or heat transfer or strength of materials, or for that matter any other subject, you should be able to teach, you should be able in a way that the student connects to his environment. Okay, the connectivity with the environment, that means the engineering is not in the book. Engineering came, then the books came. So we have to understand that the book is not where the knowledge lies. The knowledge is actually spread up everywhere. Book has formalized it. It has made your life easier. It has been segregated into chapters so that the delivery or the consumption becomes much more lucid and interesting, for example. However, knowledge is around us, isn't it? That means, for example, I usually give this common example of, let's say your finger gets burnt. You are ironing the clothes in the hostel, okay, or your mother is cooking something and you happen to touch, the hot tawa, for example, and the finger gets burnt. Okay. Now one can take this example of a finger getting burnt, and then all the equations of heat transfer, the energy conservation can be applied, and you can teach them with that as an example, isn't it? You have a mass of the object, you have some specific heat of the object, you have a thermal conductivity of the object. Okay. Then a certain amount of energy has been supplied to the system, so you can make a control volume and the energy comes in. No work is done, so that means the energy must be equivalent to the heat supplied must go eventually to the internal energy of the system. So dq is equal to du plus dw. There is no dw, so dq must be equal to du, isn't it? And then what does that du do? Naturally, there is a rho and there is Cp, and so that there is a delta T. So it's a fixed temperature system, and there is a big body which is isothermal, and a small portion has been burned, so you can take it as a semi-infinite type of an object, is it not? And then the heat comes in, the temperature rises. Okay. Now there is a pain threshold beyond which you start feeling uncomfortable. So now as a transport engineer or as an engineer, what is your job? You want to get rid of this extra energy and bring down the temperature. How fast you can do it is what you are looking at right now. Sometimes you have to do the other problem. It's like how slow you can do it, isn't it? You want to preserve the heat. You don't want to take it out, isn't it? So what do we do? Forget about books, forget about everything else. What do we do when our finger gets burnt? Okay, we can just keep it like that. We don't do that, isn't it? We can. It will cool down. Will it cool down or not? Yes, it will. It will cool down. We can just keep it like that. And there is a certain physics by which it will cool down, is it not? Because the temperature close to the air which is close to this finger will get heated up. It will expand. There is a beta, isn't it? There is a volumetric expansion coefficient. Okay, for an ideal gas you can find it out. For a non-ideal gas also you can find it out. It will expand. When it expands, it will become lighter. There is a buoyancy force now, rho at temperature T1 and rho at the ambient. So there is a delta rho. So G times delta rho will be a force which will act on the object, and it will rise. When it rises, cold air will come in, isn't it? Now this can be formalized in a book, and you can talk about Grashof number, you can talk about Nusselt number coming out as a function of the Grashof number and things like that, is it not? That all formalization can come, but the student should understand that this damn Grashof number he already knows actually. He already knows that it can cool down, and this is how. So this is where your role as a teacher comes in. If you just derive Nusselt is equal to constant in Grashof to the power A, it will not click. It will not. The student will not become happy to learn. Okay, and then you will say, अरे attendance होता है, कोई आता ही नहीं. अरे आता क्यों नहीं? क्योंकि मिलता नहीं उसको कुछ यहाँ पे. Is it not? कुछ अच्छी चीज मिलेगा तो जाएंगे ना. You understand? So the value addition which you guys have to do is the connectivity of that equation with the outside world, which they already know actually. Even a dog knows that when his finger gets burned, when his leg gets bent, वो ऐसे ऐसे करेगा. So dog knows that if you do like that, the heat transfer increases. Is it not? Why? Because just keeping it like that, the force which was there was only buoyancy. Now there is an inertia force, there is a relative velocity between the finger and the ambient, and then suddenly it comes that Nusselt is proportional to Reynolds, isn't it? You do this, Reynolds number increases, is it not? And then yes, this is better, is it not? If not that, then what do? You put it into ice, you put it in cold water. So that means previously some air molecules were hitting this, isn't it? Now some water molecules are hitting it, and you feel better. Even if the Reynolds number is the same, even if you keep the Reynolds number same, still you feel better. Because now the molecules which are hitting, something has changed, isn't it? Something has changed. Now the same molecules, when you change the molecules, your cooling curve is better now, is it not? That means other than the Reynolds number, there is something else which has to do with the molecule itself, which is responsible for enhanced heat transfer. Is it not? Do you agree with me? Okay. Then now suppose you are still not comfortable. What do? We make it wet and then blow air. Now it is much better. So what have we done? We have changed the physics now. From single phase heat transfer, we have moved to two-phase heat transfer. We are now making use of the latent heat. The HFG was not there in the previous example, isn't it? Now latent heat has come in, and we suddenly see that the heat transfer coefficient is now much better. If you put some ethanol, and then do like that, that will be still more better, is it not? So this is where you as a teacher have to come in. Okay, you as a teacher have to come in. For example, all heat transfer. For example, your mother, when she cooks aloo, is it not? Aloo ko jab ubalte hain, then what do? She keeps it on a tap water or pani mein dal ke, and then she starts peeling off. So the temperature must be the temperature of the top surface must have come below 40. Otherwise, to haath jalega 40, 42 ho gaya hoga. Is it not? After that, to haath jalne lagega. How about the inside temperature? Is it still 100? Is aloo inside also hot enough when the peeling takes place?
Yes.
What? The temperature outside is 40, 42. What about the inside temperature? If you break it open, you see steam. You see steam. That means, can you take aloo as a lumped parameter system? No, you cannot. Is it not? Is it not? If you have a copper ball, and if you put it in water, isn't it? What will happen? The inside temperature and the outside temperature will be more or less the same. More or less the same. More or less the same. Isn't it? Huh? So now you can now with this discussion, then you say there is something called BO number. There is a thermal resistance of conduction, thermal resistance of convection, and then you describe what is the numerator, what is the denominator, and then it will come alive. Is it not? So, I mean, we take bath for example. When we take bath, if you just put the null, very small, what happens? The water stops dropping, it comes down. What is the shape of that water jet?
Like a line. Almost like a straight line.
Is it like that straight, or is it like this? Why does it become convergent? No, forget the formula, yeah. Forget formula. That's what I am trying to tell you. Don't go to the formula at the end. First, understand it. Speed is increasing. That means it is accelerating, and rho a v has to be constant. Therefore, you will see that as the velocity increases, the area of cross section will go down. After a while, it becomes unstable, and then you can get small drops. Is it not? So who is supplying the energy to give the drops? Because surface energy is needed to create drops. Who is supplying that energy?
The energy is getting converted from one.
So the kinetic energy, the inertia of the system, the kinetic energy, the accelerating kinetic energy, the gravitational pull is there, and that kinetic energy, part of it. But why does it become unstable? Then you go into then you have a Navier-Stokes equation. You perturb the Navier-Stokes equation, you create a perturbation equation, you subtract the two and have a linear theory, for example, for perturbation, and then you will come to know that there is some Rayleigh-Taylor instability. There is some sort of an instability which will grow, and when that instability grows, the nice jet which was coming will now break down, and you will have atomization, for example. So what I am trying to tell you is very simple. What I am trying to tell you is, please, whatever subject you are teaching, whether it is thermodynamics or heat transfer or solid mechanics or manufacturing process, okay, or fluid mechanics, please see that subject around you. How many of you have calculated the rate of heat transfer from human body? How much heat are we dissipating? Can a problem be simpler than that? Every day we dissipate energy. Every day we try to, right now I am trying to reduce my energy as much as possible by putting multi-layer insulation. Isn't it? This is MLI, isn't it? Multi-layer insulation. Okay. How much energy are we dissipating? Anybody? Any idea? Rough guess?
I remember correctly, it is 59 or 59.
What? 50 watts he says. Around, okay. So that's the first guess which he has made.
We can calculate on the basis of, we will assume that the temperature of body is constant.
Right.
Around 37.
7, right.
Surrounding temperature is variable of time.
Let's say it is fixed. Let's say right now it is 25.
Then we will say that
So delta T is 20 degrees, let us say.
yes,
How much is the typical area? Human body area.
We will assume that body as a cylinder.
As a cylinder, that's a very nice model. You can make as a cylinder.
Then we will assume
But forget about cylinder also. I can give you the area of the body also. No, you should know the area. How much is the area of the body? Any idea? Grown up body, how much is the area? Any idea? एक rough guess मारो cylinder लेके.
yes, we can say sir.
2 pi r L.
Yes, yes.
Is it not? So,
Then we will assume.
so this is no. I mean, I am not interested in the answer right now. I will tell you the answer. That's not. But what is important to know is that you have all MTech, all have studied heat transfer, but we have never bothered to calculate how much heat is dissipated by me. Is it not? This is what I am trying to tell you. You understand? You know how to do a differential equation, you know what is homogeneous equation, you know what is non-homogeneous equation, you can derive, you can, if the boundary condition is known to you, you can get C1, C2, and get some, some values of the constants. Okay, you can convert, you can have some, separation of variables and integrate. All that you can do. But the connectivity with real engineering is not there. That is where we have to be different, and that is why I am different. That is what you have to say also after 5 years, that I am different because I make my students connect to the real world. You understand? I still remember my first interview was in ISRO, in a campus interview. Okay? I entered the room, there was this door, and I pushed it and I entered and I sat, and then after some discussion the person asked me, please tell me an example of combined loading. Okay. Now a typical student will start thinking combined loading means beam banayega, uske upar kuch wo karega, point load, this load moment. I just told him that I just entered the room, the handle I had to give a torque and push. Combined loading. Is it not? This is what I want you to do. And then you will be a good teacher. You understand? The student must be enthusiastic enough after your course that as soon as he starts going out, he starts looking everywhere. Kahan fluid mechanics dikh raha hai mere ko? Kahan heat transfer mere ko dikh raha hai? Is it not? Extended surfaces, fins we teach. Is it not? We see fins everywhere. Is it not? Whenever we are feeling cold, we sit like that. When we are not feeling cold, is it not? जब गर्मी होने लगता है. So is it not finning system? Am I not extending my area? Is it not? So why don't you take this as an example? जब मेरे को ठंडी लगता है तो मैं ऐसे हाथ करता हूँ उसको. If there is a fire here, I don't put hand in line with it. So there is a shape factor. Is it not? ऐसे ऐसे करता हूँ, धीरे धीरे गर्मी बढ़ता रहता है मेरा. तो वो शेप फैक्टर के लिए वो चित्र बना के वो ओमेगा एयर या वो बाद में करो, वो करना है. आई एम नॉट अंडरमाइनिंग इट. आई एम नॉट सेइंग दैट यू डोंट हैव टू डू दैट. यू कांट ओनली टॉक. दे हैव टू एनालाइज ऑल्सो, दे हैव टू अंडरस्टैंड. बट देन which equation to use when, which boundary conditions to apply, what are the assumptions under which this equation will be valid. Okay? And the spark which comes that, oh, this can be solved like this, can only come if the teacher has done the due diligence, that he has made his students aware of the connectivity of that equation, the terms of that equation with real time situations. Okay? So if you want to do it, it's hard work. It's not easy. See, right now what has happened is, unfortunately, those people who don't get anything else in life, they want to become teachers. I mean, we are all part of the same community. Is it not? But then once, fine, that's also fine. You never got anything else, now you want to become teacher, that's also fine. But once you want to become a teacher now, then everything which is needed to make that profession worthy of it, and you enjoy, your teachers, your students enjoy, your colleagues enjoy, is what now you have to do. You have to inculcate an interest, if the interest is not there. If the interest is inherently there, then there is absolutely no problem. Is it not? Absolutely no problem. Okay. So coming back to that question, So, is radiation important when heat transfer takes place from human body? Why? Normally people say that radiation is only important at high temperatures. We are not high temperature. So, why do you say radiation is important? Hemalay.
Sir, actually every body which have temperature greater than 0 Kelvin will emit some radiation.
Some radiation, perfect.
Radiation is a parameter of temperature with temperature, where temperature is, where energy is directly proportional temperature is to the power 4.
Forget that, but how, why is it, why do you think it is an important thing when you are doing a human body calculation? If I am going on a motorcycle, I am doing a calculation for the heat transfer from the engine fins, I do not care radiation, the temperature is much higher there. But at human body the temperature is only 37, but we
The temperature range within which humans can sustain
Comparable
no,
comparable bands.
yeah, comparable to
Natural convection.
absolutely. So, what, so the idea here is that there are several modes of heat transfer, okay, and all of them are probably playing a role all the time. Is it not? Most of our systems have convection, conduction and radiation. For example, this building right now, all of us are sitting here, there is radiation, there is convection, there is conduction naturally, okay, in the human body. So, everything is important. Now, which one to assume negligible or which one to focus on will depend on the relative magnitude of the things. Is it not? So, in a human body example, the natural convective heat transfer and radiative heat transfer are almost equal, and your answer has to be multiplied by 2. Yes. Okay, you do the calculation. You understand? So, this is what I want to stress. You know, in half an hour I cannot tell you everything, okay, but the underlining, let us say, message, the take home message which I want to give is that make an effort so that the equations which you derive in the class come alive. Talk about examples which can be related to that equation. Okay, that equation is not a dead equation. Otherwise, the same equation can be taught by a mathematics student also, a mathematics teacher also. Is it not? It is the same differential equation, no? Let us say energy equation or partial equations which are Navier-Stokes equation. It can be taught by a mathematician also. So, why is a mechanical engineer being asked to teach that equation, to derive that equation? Okay, boundary condition, Dirichlet boundary condition, you can write it. But do you know what is Dirichlet boundary condition in terms of temperature? How do you achieve it? Which systems are there around you wherein insulated boundary condition is really working, or is it really possible to have an insulated boundary condition in real time scenarios? How close can you go to a insulated boundary condition? When you say convective boundary condition has H is equal to 10, what does it mean? What is that 10? How many systems are there which have H is equal to 10? How many systems are there? You have a PC, for example, there is a fan at the back, isn't it? What is the H in those systems? Is it 10? Is it 50? Is it 200? Is it 2000 watts per meter square Kelvin?
Around 2000.
See, there is one order of magnitude coming in this class itself.
No, it must be around 50.
It must be around 50.
50 to 100.
You see, 3 answers have come. This is important. Please try to get real time values, and that is why I said some of the books are good. These books have examples, these books have problems wherein the value which has been taken is not just because कुछ भी दे दिया, ऐसा नहीं है. All these books, the good books, will always assume values which are very close to real time technological or real time industrial problems. Okay? So, it is very important for you to get hold of these books, solve these problems before you go to the class, and then get a feeling of what is 100 watt, what is H is equal to 20, which are the systems where H is increasing, what do you mean by low Prandtl number systems, what is the meaning of high Prandtl number systems. Okay? If an engine oil is falling down a hot wall, is it a low Prandtl number system or a high Prandtl number system? You have to keep thinking about it. If you do that, then your teaching will come alive. That means people will be happy to come to you, isn't it? And then there is no problem of attendance or anything, is it not? So, I think I have run out of my time. No, that's okay. Malay is already here. So Malay will also discuss a few things. He is also a fantastic teacher. He has also taught large classes, fluid mechanics, not thermodynamics, no, thermodynamics also, fluid mechanics. So he has taught large classes, 450, 400 students, like 380 students, fluid mechanics. I have taught large classes with thermodynamics. Okay, so that also requires enormous amount of planning. Okay, Malay can give a lot of ideas about how to plan for a class, because the course is wide, everything has to be covered, and interest also has to be simultaneously, let's say, it has to be kept alive. You cannot leave anything also, and they are young students, so you have to give them a lot of assignments. You have to make sure that they are doing it. You have to take a quiz also in between, and there are only 40 hours or even less, 35, 36 hours which we get in a full semester. So teaching fluid mechanics in 35 hours with lot of interest, lot of examples and derivation and whatever I have told you, how to make it alive and things like that, is a very, very challenging job. Okay, an enormous amount of time has to be spent before you go to the class. And Malay will also agree, every class is different. The same topic, Bernoulli's equation, every time you go, you have to think, you have to work, you have to, how I am going to pitch it, what diagrams I am to, there are 3 blackboards, which blackboard I am going to use, how, when, all that has to be planned. Otherwise it goes haywire, is it not? So that delivery is like a program. It's like a some actor going and it's like it's an act, and every actor wants the full impact. Okay, so you don't go to the class just like that. Okay, so plan out things, read these books, talk to the students, and before that you get hold of all these numbers. What is 100 watt? If I just do like that, how much wattage of heat is coming out? Is it not? हाथ पे हाथ मलते रहेंगे तो कितना energy निकलेगा? You should have some feeling of that. So assume a friction coefficient. Okay, think what is the velocity? Is it not? And the weight of the hand is known to you more or less. So you can find out a work done, and all the work is now converted to heat. Nothing is happening. Is it not? So it will increase the temperature. Okay, so these are things which you have to do, and that will then make it you a unique teacher, so to say. Is it not? Everybody will be happy to come to your class. So with this, I thank you, and I invite Malay to continue.